So we've done a little bit of talking about momentum, and now we're going to see some examples of when we would use momentum. We talked about impulse and using that to solve problems. We're going to look at examples where we would use momentum to solve problems. So we have here an astronaut with a mass, has an oxygen tank with mass, and he's going to push the tank away from himself or herself with a speed of 2 meters per second, and the astronaut will recoil in the opposite direction. So if you can imagine, if you're floating in space and you push off of something, and as you push off, you kind of get pushed back in the other direction. Okay, and so, I mean, if you think about Newton's third law, this is an example because you exert a force on the tank, and the tank exerts a force back on you. All right, and it says that the tank is pushed away with a speed of 2 meters per second. Okay, so it would be very difficult to answer this question using any of the techniques that we have so far, because we know that the tank is pushed away, we know that it started from rest, we know that its final speed is 2 meters per second, and we know that it has a mass of 10 kilograms. We also know that the force on the tank and the force on the astronaut are about the same. So if they experience the same force, what we could do is figure out what force would cause the tank being pushed to develop that speed, and then we would use the same force on the astronaut to see how fast the astronaut was going. That'd be pretty difficult to do because we don't have enough information. We could use it, we could set up this problem and solve it, and some of the missing variables would drop out. But this is one of those times where it's actually easier to use momentum. And so here we have the astronaut, and then here's the tank. He's going to push it away, so it's going to go this way at 2 meters per second, and the astronaut's going to get pushed back that way. Now, as we do this, I want to think about for a second Newton's first law. So according to Newton's first law, if these two things together, the astronaut and the tank, was our object, what Newton's first law says is that the object this object is at rest, and according to Newton's first law, it's going to stay at rest unless it's acted on by some external force. So unless you have like wind coming in this way and pushing on it, or you have like something coming this way and crashing into it, nothing's going to cause those to move. They're going to stay exactly there. They're located around their center of mass here, okay, unless something causes that to change. So something, just like we say this box is sitting here on a table, it's going to stay sitting there unless something exerts a force on it, okay? The same concept here, except there's no box. It's two objects instead of just one, but the Newton's first law still applies here, okay? And that's why we can use momentum. We can say, okay, well, if I look at the total momentum of the system, it's going to have to be the same before, and it's going to have to stay the same after. Okay, well, it turns out that just because they're at rest doesn't mean they can't, like if he pushes off of it, it's going to have motion, but that momentum will still be conserved. Okay, so what we would have to do here is we'd have to find, well, what's the momentum before for each object? And then we're going to compare it because it has to be equal to the momentum after for each object. Okay, so in this circumstance, both the astronaut with a mass of 80 and the oxygen tank with a mass of 10 have a velocity of 0. Okay, so the total momentum of the system, in our system being these two objects together, our total momentum before is 0. And so now we're going to compare that to our momentum after. Well, we know that the tank is being pushed away with a speed of 2 meters per second. So we don't know what the speed of the astronaut is. So we'll say 80 v. And then for the tank, we have 10 and with a velocity of 2. And we'll say this is positive 2. Let's say that this way is positive. Okay? It's a positive 2 meters per second. And now our goal here is to find, well, how fast is the astronaut going after they push off? Okay? All right, so we do our calculations, we do some algebra, and we end up with the velocity of the astronaut being negative 0.25 meters per second. So we have this tank going this way at 2 meters per second, and we have the astronaut going this way at negative 0.25 meters per second. Okay, and what you'll find is the total momentum of the system is still 0, because 2 times 10 is 20, so we have a positive 20 momentum from the tank, and 80, the mass of the astronaut, times negative 0.25 is negative 20, giving us a total combined momentum of 0 still. And so what you'll find is that the center of mass of this system is going to stay right here at that same spot, even though the astronaut's now drifting this way and the tank's drifting this way. That the center of mass of the system, or the average location of their mass, is going to stay the same, and it's not going to move. Okay? And so here's an example of momentum conservation. Okay, we're going to look at a second example here. In this case, we have a train in which we have an empty boxcar that's coasting along, and it's going to hit this other boxcar, or this loaded car that has a mass of 55,000 kilograms that's kind of sitting there at rest, and they're going to kind of like latch together. Okay, and if they latch together, that means that they're going to have the same speed and they're going to be moving along together. All right, and so this again is a problem that we can very easily solve using conservation of momentum. And if we were to try to use forces, it would just be much more difficult, because we'd have to think about the amount of time the collision took. We'd have to think about we'd have to kind of estimate and do some guess and check to figure out where the speed ended up. It'd be a little bit tricky. And so this is something where it gets a little bit easier if we just look at momentum. Okay, so we have the momentum of our initial car right here. Okay, this guy moving along with a mass of 9,000. We have our momentum of our second car here that's at rest. Okay, and then afterwards we have the momentum of each. Okay, but since they're going the same speed, that means that this V and this V are the same. Okay, and so we can rewrite this as m plus m times v, and the reason why is because they're traveling together. Okay, so in the beginning we have this guy has a mass of 9,000 kilograms and a velocity of 3. This guy has a mass of 55,000, a velocity of 0. Okay, they bump into each other and combine, and so their total masses add up together, and then we would multiply that times this final velocity, and what we have here and what we have here would have to be the same, because that momentum is going to be conserved. Okay, so go ahead and punch in those numbers and find how fast the cars are going together after they collide. Okay, so we punch in our numbers, we get a total momentum of our system of 27,000 kilogram meters per second. We'll divide that by those combined masses and get a velocity of 0.42 meters per second. Okay, and so this is how fast those trains are moving together. And actually for this example, this is also the velocity of the center of mass. Remember that the velocity of the center of mass is the total momentum of the system divided by the total mass. Okay, so here if we take our total momentum and divide by our total mass, we get the velocity of our center of mass. And the reason that's true here is because those trains are stuck together, moving together, and so the speed of them combined would be the same as the velocity of that center of mass.